Hey guys, what's up? Eddie Aho here with KissAnalog.com. In a moment here, I'm going to present another interview with Mike Engelhardt, the creator of LT-Spice, and now the creator of QSpice. Now, QSpice is a new improved version of LT-Spice. You know, after having so many years developing a tool, given a chance to develop a new tool, this new QSpice looks like it's just really taken off. Today's interview, or talk with Mike, he is going to show us a new part of the tool that he's presenting. It's not coming out for another week, maybe. So we get the first look at this. So it's pretty special. It's pretty special to have Mike on. And it's pretty special to be the first viewers of this new tool creation. Now what it is, it's creating models. So any kind of transistor really, it's a, whether it's a FET or JFET or even diodes. Now, what's really neat about this tool, in the past, what I've done is when I try to create a model, if I can, I'll download the model, but then I'll go into each parameter and I'll set it and everything. And hopefully what that's going to do is make this model representative of the real device so that it'll reproduce those curves that we see down below. Well, this one's really cool. The way he's doing this is you get to put in information, but you also get to look at the curves and show the tool what the curve is supposed to do. So then the model can extrapolate that information and say, oh, okay, so to do that, I have to do this. And so I just think it's super cool. Let's get into this. He's going to show us how to do it, and really exciting. And man, just feel really privileged to have a chance to talk to Mike again and to present it to you guys. So subscribe if you haven't done so. Like the video. That really helps a lot, guys. And share this video on LinkedIn, on Facebook, whatever have you, because this is one of those things that is going to help raise QSpice awareness. It's a brand new, I want to say brand new. I think my last interview was just over a year ago, but this tool is fairly new, but they're doing updates practically daily, and it's come a long ways, and it's free. So we always like free, good tools, right? Free bad tools are just a waste of time. This is a great tool. So, all right, let's jump in this interview. Hey guys, what's up? Eddie Aho here with KissAnalog.com and Mike Engelhardt. He's a wizard behind LT-Spice and QSpice now with Qorvo, right?
Yes.
So
thanks for having me on, Eddie. It's great to see you again.
Yeah, it's great to see you. And I like your background there.
Yeah, otherwise it'd be scuba equipment, because I like to dive.
I was tempted to wear your T-shirt, your new T-shirt.
Oh, you have a new T-shirt?
I do, but I was afraid you didn't want to look at yourself all.
Oh, I'm okay. Well, where I draw the line on that is when I'm doing a seminar, and if at the front of the room they have pictures of me on the wall, it makes me feel like I'm some, communist dictator talking or something. That's where, that only happened to me once, and it was disturbing. It definitely gave me pause. But the T-shirts, I don't worry about.
Well, you get around, right? I mean, you're traveling quite a bit. As a matter of fact, you're traveling tomorrow, aren't you?
Actually, it's a week from tomorrow, so I think we had a little date mixed up. Yeah, a week from tomorrow, I'm going to Nuremberg for the Embedded World trade show.
Okay.
And then I come home for one day, and then I go to Atlanta for the APEC conference in Atlanta.
Okay, well so you're keeping pretty busy.
I am very busy.
It's been a while since I've been to that conference, APEC. I see there's updates all the time to the software. It's just growing fast. There's been people, more and more people are asking about it. And it seems like, the tidal wave's starting.
Yeah.
It's growing fast, I guess.
Yeah, there's updates, maybe not every day, but every week. if you don't see updates for a few days, it's because I'm working on some skunkworks project and I have the code taken apart and I don't want to push what I have now with a half implemented feature in it. Unless there's a bug report that I go back to an older image, fix the bug, incorporate the bug in the forked project in the release version. But
Okay.
yeah, there's a new version every day, 7 days a week.
Yeah, I've noticed that. I hate to say it's every day because I don't check every day, but it seems like every day I check, there's a new update.
Yeah.
So, but you've got some new stuff coming that you want to
Yes.
talk about.
Yeah. So the biggest thing that we're talking about now is the fact that you can make models from data sheets. And
That's huge.
yes, so these are for discrete devices. If you have a power MOSFET, there's a tool that will digitize the data sheet. The output characteristics. You put in the quantitative information about the RDS on, and it will make you a model that will match that RDS on and those output characteristics. And you can match the gate charge required to turn the thing on. So you will reliably have a model of a power MOSFET that will give you the right ohmic losses and the right, Miller capacitance, and you'll know whether or not you can drive it your circuit. It'll be a valid go no gauge in your simulation whether or not that transistor will work where you want it.
Okay,
And we've
that's
also done that so that's the biggest model generator. The tools that are in there have been plumbed out to two other tools. One is just for doing diodes, which is similar to just the body diode of a power MOSFET. But diode data sheets are not always spec'd well enough in capacitance. So the diode model generator will be forgiving of missing information. If you don't have a plot of the varactor capacitance versus reverse bias, it will you tell it at 0 volts with your LCR meter, and then it will, dead reckon what it probably is well enough.
okay.
So there's there's that for the diodes. The diodes are they're forgiving of missing information. It will just guess what you don't have, and it'll honestly, for initial design work, it'll absolutely work very well. And then it will also generate a model for a JFET. And the JFET data sheets, this is more of a cultural thing in electrical engineering, that JFET's data sheets aren't complete enough to make a really good model. But between the data sheet and a DC LCR meter, you can make a good model of your JFET, and
Okay.
it will have, you know, without characterizing the shot noise, it will dead reckon, what the noise would be from first principles, that it can't be less than this. It will compute that, where most SPICE programs actually get that completely wrong, by orders of magnitude in the triode region. The noise of Berkeley SPICE doesn't handle the noise of a JFET in the triode region at all. It just ignores it, basically.
Yeah, I had a problem with I did a JFET preamplifier one time, and I couldn't simulate the noise, the shot noise and whatever other noise that's coming from the JFETs. And so it was digging into data sheets trying to figure out which JFETs I should use. And it was mostly a lot of trial and error.
Okay, well, the QSpice JFET model generator should give you a pretty good handle on the noise of a JFET, because it will
Okay.
take care of the gross error. Now, flicker noise, it won't automatically do. You could, decorate the model with some flicker noise information if they have that on the data sheet. You could probably get it, but at least it won't make a gross error of the noise vanishing in the triode region. That it will handle correctly. In fact, the right now I'm actually talking on a JFET amp I use. I have this SM7B microphone, and my channel strip certainly did need some extra gain. So I have uh, um, I simulated and designed a JFET amp for the thing. Similar, the circuit is similar to what's in a FET head. I don't know if you know pro audio stuff, but there's a
Yeah.
commercial product from Tritian called a FET head, and there's another one from Cloudlifter. The Cloudlifter one I didn't like because it ran the JFETs in Cascode, and the patent was done in LT Spice, and it was from a date when it didn't have the triode noise right. So there's no way the Cloudlifter has as low of noise as a properly designed circuit um, like the FET head. So I used more of the FET head design, except that the FET head doesn't terminate the mic in the way I like. You really don't want to put the termination, from plus to minus. You want to put from minus to ground and plus to ground. That way you short out the common mode noise, because you
Okay.
have this dynamic mic, which is a little antenna. You want to just short that out as much as possible. And the differential gain, you just want to the differential mode, you just want to dampen enough to kill any resonances in the mics. You want it a few times higher than the natural impedance of your dynamic mic.
Okay.
So that's what I'm talking on right now.
Yeah, that sounds great.
Let's see. I don't know. The cable isn't quite. It's built into a cable, and the cable isn't long enough to show you the fact that I have brass shim stock wrapped around and soldered together, and then Gorilla taped over to make my electric enclosure for it.
That sounds very professional.
Oh yeah. Nothing but the best.
That's right. Nothing but Gorilla duct tape with.
Hey, don't ever estimate brass shim stock. I mean, you can solder to it easily because it doesn't have the thermal conductivity of copper, and it's a fantastic, Faraday shield. So
Oh,
yeah, there's nothing like shim stock for making electronic enclosures.
wow. I have to look at that. I never even thought about that.
Yeah.
But yeah, the model that's big because a lot of people are trying to build models, and I need to do some videos on that. I have this amplifier. It's an old amplifier. It's all FET, and it's a design from Erno Borbely, I think it was his name, a German, long time ago. He's probably not around anymore, but I still have an amplifier, and I just uncovered it the other day, and I thought I want to put this in. I want to put this in Spice and simulate it. Because I like
you'll probably have missing models for the semiconductors if they're old semiconductors, and you can make your models for it.
Yeah, and then back in the day, I remember being really good. So I just want to revive that design and maybe update it. So Spice is always a great place to start. As far as the library, I haven't gone through that new tool. Is that released yet?
Yes. Well, it was released quietly, and then next week there'll be press releases on it.
Okay.
If you want, I can show it to you. Maybe we can capture.
Yeah, that'd be great.
All right, let me figure out how to share my screen here. Let's do this. No. Nope,
that's one of probably the biggest comments I get is how to create new models.
So can you see my screen?
I can.
Okay, good. So this is QSpice.
Okay.
I probably should have reduced the resolution to 1080p. It might digitize better in your video, but in your content. But anyway, so this is QSpice. Looks normal. And you go into File. There's this thing called Model Generator.
Okay.
And these are different executables in the program's files QSpice directory, but this is just so you don't have to have you don't have to clutter your desktop up with extra shortcuts. You can just find it here. So model generator, here's the MOSFET thing. And, it jumped up on a different monitor. So that's the tool. And I just used QSpice to launch this thing. And, we can make a model. Here's a alpha mega semiconductor power MOSFET, and you fill out the information. Okay, well, model name is still there. I guess I did this one, so I guess I'm cheaty because I actually have made this model before. But you fill out this form. Some of the information is just annotations, so that if you put it in a library, you have some selection guide information about picking this model. If you make a whole bunch of them, you want to say, well, will this handle the current or the voltage? So all this information has been filled out. There's two numbers here that you have to guess, and if you don't like the model, you can change them and see if you like the model better.
Okay.
Data sheets usually don't have high enough quality output characteristic curve traces in order for them to extract these parameters. So basically, this R external divided by R external plus R channel is how much of the resistance is due to something other than the actual channel, and how much is due to the lead frame and the bond wires and the distance from the pad to the channel. In a MOSFET, that's where most of the resistance is. It's not from the channel itself.
Okay.
If you say that the RD divided by RD plus RS, you say it's symmetrical. That's going to be roughly about right for a power MOSFET. Even though they're vertical devices, it's not a big difference.
Okay.
You would maybe change that if you want to match RDS on over current, because you might want to put more or less current in the source resistance so that the RDS on increases more dramatically as you put more current through it, because what happens is that if you have more current through the source resistance, you gobble up the enhancement voltage and you're starting the thing off. So that's why you can that would be the number you would vary to change that. This reverse recovery charge is on the data sheet, and then you have to say how much current that reverse recovery charge is at. Now, this number is that you have to pick off in a little bit weird way. Okay, so this is a zero biased output capacitance, and you have to find a curve that looks, okay, here it is.
Okay.
Here's the output capacitance. You look at 0 volts, and this looks like it's about 2.6 nanofarad, and that's what I put in there, 2.6 nanofarad. Okay?
Okay.
So that's just filling out information. Some of this is electrical information. For example, this RDS on will be precisely matched. And so you have to give it the voltage that was enhancing the gate at that RDS on, and you have to tell it the current so it knows how much source degeneration you have that reduces the enhancement voltage. So these three numbers are very important to get in there to match the RDS on. Okay, now we go to the next pane. And we want to digitize the output characteristics. So we look for the, curve trace of the part. And we actually digitize this thing. All right, so I like to get it nice and big on the screen.
Okay.
And then I don't want to move it at all, because I'm going to calibrate the screen and digitize points from this, and then I'll extract these points. So here we have to set up the axes. This is going, so we look here, it goes from 0 to 100 volt, and it's a linear region. So I have to set up this axis to match. So it goes from to 100 amp, and it's a linear range. The horizontal axis is 0 to 5 volts, and it's also linear. So this is 0 to 5, and the log this box is not checked. And now I have to say where the origin is in the upper right-hand corner. So you press this button, you'll notice that as I move the mouse, it's reading out the pixel that I'm pointing at.
Right.
This is negative because I'm on my other monitor,
Okay.
So anyway, now, if I point at this, if I come over here and point at the data sheet, you'll see the cursor looks like a little text caret. Can you see my cursor? I'm moving it a little bit. It looks like a text caret.
Okay.
And if I move the cursor over to the other side, it looks like an arrow. So that's a little disconcerting, because I want to point at a particular pixel, and my cursor type is changing depending on where I point at the data sheet. So I want a crosshair cursor. So what I do is I point at this application, and I just messed things up. I have to cycle through this. I'm going to start over. I point at the application, and I press the mouse button down. Now I have a little crosshair cursor that will XOR with the pixels on the screen, and I keep holding the mouse down, and then I can move over to the PDF, and I still have my crosshair cursor, and I point at the pixel I want. It's XORed at exactly the origin, and I release the button. So the digitized point is when you release the button, not when you do the mouse down. And the reason for that is kind of a Windows security thing. One application cannot change the cursor in another application. But if you mouse down someplace, then that application has locked the cursor. It owns the cursor. So I come back, I need to digitize this point. So I come back here, mouse down, I got my cursor, I point at this corner, and there it is. So this tool can now knows exactly how to read out any point here to the voltage and current. Now I have to give it 3 points. On this little curve here, it shows you a little cartoon about which three you're looking for. You want 2 to get the the impedance in saturation, and then these 2 points will give you the how the transconductance changes with enhancement voltage. So we say point 1, So you see 0.1 button is changes. I move the mouse down, come
Right.
over. I'll come over to, I'll use this point and this point. So I point at this one, mouse down again over here. I point at that one. Now I need 0.3. That was a very important thing. I have to say what the gate voltages were. So I used the 3 volt, the 3.2, but since I had digitized this, this is still reading 3 and 3.2. Now I
Okay.
say crunch, and that's the the model, and it's reading out the RDS on for these different gate source voltages that were different than the one that you said you need to match at
Wow,
the
that
on the
is
first page.
cool.
And then you'll really like this. There's this button called test, and you press this button, and it will start up a QSpice simulation that will let you duplicate your output characteristics. Let's look at that. Let's try to get these. So this vertical range is right. You see that this point lines up with that, and this point lines up with that, and they have about the right slope. Now, one thing I want to point out here is that in this, okay, so the slope here is correct because we said what RDSon we wanted. This is the triode region when the transistor is on and it's working like a resistor. And the saturation is correct. But in between the two, this doesn't match that well. Now, the alpha mega has a pretty good enough data sheet. You could probably extract characteristics that would match this region better. The tool won't do that. But, honestly, if you go get a MOSFET model from someplace, nobody matches the quasi-saturation region. And the tool just doesn't do that. This is trying to make a model that will tell you whether or not it will work in your circuit. And it's trying to be robust with the information, which is typically available in MOSFET
Yeah.
data sheets. And usually most vendors don't digitize their output characteristics well enough to be able to extract parameters to cover the quasi-saturation region. All right.
Wow,
So that's the output. Now let's do the
pretty
body
cool.
diode. Okay, this is the body diode here. And again, we need to set up these axes to match. So this goes from 10 microamps to 1 amp. And I've set that up. It's still checked at log. The horizontal axis is 0 to 1 volt, 0, 1 volt. So these axes are still set up. Now let's make this as big as possible so that I can more accurately digitize the thing. Or I have to say what temperatures these are. 25C and 125C. There's 25 and there's 125. And now let's calibrate the plot and then digitize, we use this 5 points. So lower left, mouse down here. And that's the lower left-hand corner, the origin. Now upper right, digitize that point. Now all of this now it's real important I don't touch this plot because if I move this thing, it won't digitize correctly. So these are the 5 points I want. 1, 2, 3, 4, 5. So press point 1, get the crosshair cursor. Now we want point 2. Now we need this, point 4. And point 5. And we crunch that. And then we can test this too. So that's our body diode. This looks rather like that. And those 5 points are perfectly matched. Okay?
Okay.
So that's the DC. Now let's do the Miller capacitance. Go to the gate charge pane here. And we have to find the gate charge curve. All right, now the way this data is extracted is they put a constant current into the gate and plot the gate voltage while switching so much current at so much voltage. That's the way it's extracted. So this is labeled in charge, how many coulombs you put on to get the gate, voltage. And if you want to use 5 volts here, then you need about 24 nanocoulomb. You got to put 24 nanocoulomb on the gate to get the gate voltage to 5 volts to make sure it's fully enhanced. Okay.
Right.
All right. So again, we calibrate these axes 0 to 10, 0 to 10, 0 to 50 nanocoulomb matches there also. So now we digitize the plot, origin, upper right hand corner. And now we have to do these 3 points. And I try to imagine the asymptotic intersection of the 2 straight lines sections I'm making to be about there. This one would be about there, and then 0.3 is here. And let's crunch. That's the full model. Let's test it. And that looks about like that.
Wow, that's crazy.
And now the model is actually on on the clipboard, so I could just paste it into a schematic, and that's the model,
Oh,
and you're ready to go.
I love
Or
it.
and it's showing you the model here. You can do Control A and highlight it and paste it yourself someplace else and build a library that way. But that's how easy it is to make a model. There's a bit of a story here. I have had a side business of making MOSFET models for various semiconductor manufacturers. That I developed tools, a primitive version of this that I just kind of kept to myself. And it didn't quite work right, but I could use it myself. It was, it was good enough for my business. And then I realized that I thought that there was a theoretical problem in the way I'm extracting these parameters because it's using this ad hoc, you know, Manhattan meander through the parameter space to match the curves, and it didn't quite work right. And I figured, well, I have a theoretical problem that I don't feel like fixing because it's too useful the way it is. I can fix any problems later in post and be good to go and fill my purchase orders, well enough. And then, it occurred to me that it was just a bug in the code, and I fixed it. And then I just decided, we're just going to give that away. We're just going to include it in QSpice. So that's the backstory behind the business model of it. But it is useful, you
That,
know.
that is super cool.
Yeah. So that's the
Yeah.
deal. That's the
Wow.
thing that will be announced this week. So you're like the first person to know about it. So,
Well, we're going to spread the news.
illness.
No, I appreciate you showing us how to do that because that would have, yeah, that, it's a lot easier to watch somebody else do it than follow them.
Yeah. There'll be some videos and the press release I think is on the 5th of March.
Okay.
I think that's the date it goes out, but I don't want you to feel embargoed. As soon as you feel like you got this this content we're making now in shape, throw it out, let people know.
Okay. Great. Thanks. Yeah, this is gonna be exciting. Well, I'll tell you what, this I've got a timer on this thing. It's we're just running out a few minutes here. But hey, Mike, I appreciate you showing us how to do that. That's big. That's going to be really cool to a lot of people that have tried to fit those curves before because you haven't been able to do it before.
Yeah,
So,
and there is um there's a fair amount of information which it can dead reckon pretty well for you. That is specifically, it adds some sub-threshold conduction. I've made enough MOSFET models that I know they have sub-threshold conduction, and I know the parameter, it doesn't vary by a factor of 2. So I just throw in some sub-threshold conduction.
okay.
And there is a temperature coefficient for the threshold voltage. Again, I've modeled so many MOSFETs. I have an idea where the current industrial MOSFETs have for a threshold voltage TEMCO, and I just throw that in. So it'll be a little bit better than the small amount of information that you extract there,
Okay.
and it will definitely let you design a circuit and determine whether or not that FET will work in your circuit. That is,
That's
there's nothing to negotiate there. That just works.
I love that. That's cool. So I'm excited to try to use. I want to build that amplifier and use. I've had people ask me, "Well, I can't get this FET anymore. I need a new FET," and all I can do is match up data sheets and it takes a lot of work to do that. But it's nice to be able to show somebody in a simulation that look like what you did,
Yeah.
like I can redo that curve.
Yeah.
And
Now,
so,
the tool is very much geared towards making a model from data sheets, and so it uses the information that's available on data sheets typically, and it tries to be forgiving if data sheet information is missing. For an older part, um, it Well, for a MOSFET, it'll work great because MOSFETs are actually one of the newer types of transistors, and so there's a cultural thing that you just about always have enough information on the data sheet to make the model. But for diodes, you know what? A lot of them don't give you the junction capacitance at all, not a number. Like an LED, but you can't put an LED in a simulation without junction capacitance because you can't put a nonlinear element in a simulation without some parallel capacitance, or you can't solve the circuit because you have
Yeah.
to go to shorter time steps to use the previous time step as a better approximation for the current time step, so the Newton iteration conversions. And that's not a problem in real life because every nonlinear element has capacitance in parallel with it, but you just can't simulate a diode if it doesn't have capacitance, not dependably. But that's
Okay.
okay. Use your Handtech digital LCR meter like you reviewed, and turn the amplitude down to 300 volts, and measure your CGA, your zero bias junction capacitance, put it in, and you're good to go.
Okay, that's great.
Yeah.
Well,
JFETs tend to actually be even worse. You might have to measure more data from the JFET. There are JFET data sheets out there that don't have output characteristics, not a single plot.
yeah,
So
I remember that when I first started working with JFETs, it was so tough. Like you had to,
yeah.
yeah, I
Um,
making jigs to test those things
yeah.
back
And
in
with
the day.
bipolars, I don't even address bipolars because there's not nearly enough information from any data sheet from any bipolar to make a model. It's just that you have to go into a lab and measure a bunch of data and do it. So I'm not even addressing bipolars.
Okay, yeah, I and I still have a curve tracer over here.
Which one?
I have a couple actually. I have an old Tektronix and a leader.
Mhm. Well, I have curve tracers, but I actually make my own because I want pulsed data. Even for a small signal FET, you need to pulse it because you can't let the temperature change. You have to fit the device equations with the transistor, completely at one temperature. So even
Yeah.
for small signal FETs, I use a pulsar. I have a very high quality curve tracer. If
Well,
you
hey,
got time, I can show you the schematic here if I can find it.
all right, guys. So, what do you think? Hey, I have to apologize. I was using a free version of the tool, the meeting tool, because I wasn't sure if I wanted that one. I used another one in the past, and I actually like it. It worked really well. And anyway, it was a work day too. So I was doing this on my lunch break, and so I was kind of limited on time. So I thought it was going to be okay, but I wish I could have just gone longer because Mike was going to show us a schematic of a tool that he made, a curve, essentially a curve tracer. So maybe we'll get it back and we can go look at that stuff. And guys, he alluded to the Handtech LCR meter that I reviewed. So after seeing a review, he went out and picked up on these, and he's happy with it too. If you need to look at capacitors or inductors and figure out their curves over time, because inductor's just not an inductor, right? And a capacitor's just not a capacitor. Both components have parasitics of L's and C's and stuff, so it makes the curves not just a straight line for X of L or X of C, right? So if you're really trying to do a Class D amp, crossover, or any kind of filter, it's nice to actually look at the real curves, and you can look at different frequencies. So anyway, just I just thought I'd mention the Handtech tool since he brought it up. But all right, guys, hey, thanks for watching. Give a like to the video. That really helps. Share it. Subscribe if you haven't done so. And thanks, Mike, for being on the show and giving us the first look at this new powerful, really super powerful modeling tool. And looks like, I mean, it's great to be able to see how him showing us how to use it, how to hit the points of the curve, and how to input that information versus a trial and error type thing. I haven't gone through it myself without looking at his video, so but I'm sure now that I've seen his seeing how he did it, I could do it. It looks like it's a pretty darn nice tool. So, all right, guys, thanks for watching, and thanks, Mike. Thanks, Corvo. And hey, guys, by the way, if you watch this long, put a comment down below. I'll pick a viewer that Qorvo will send out either a t-shirt or socks. I think they have XL or double XL t-shirts left, or they have some cool Qorvo socks. So if you want one of those, like the video, be a subscriber, and send me an email, okay? And I'll do a raffle and I'll pick a winner, okay? All right. Hey, thanks for watching, and we'll see you next time.